Hello, so are you hungry? So I have good news for all of you. So after my session, you can have lunch. So first, thanks to the organizers of Reels Pacific for inviting me to the conference to share my experience. Like what I talked in yesterday's panel discussion, becoming a senior developer without solid and broad knowledge, we can't become a senior developer. This year, Reels has turned 10 years old, and it's still one of the best framework in the world. And the core team keeps adding the best work practice into the framework. However, nowadays, we hear more and more voice saying that Reels is not for beginners anymore. It's true and not true. It's true because there are so many background knowledges besides Reels we should know. It's not true because Reels really did a good job to hide those details. Whatever, if we want to turn senior as architecture, we must and should learn those knowledges, such as operating system concepts, database system concepts, fundamental compiling attacks. Today, my topic is about database with Reels. First, let me introduce myself. I'm Ye Dingding from mainland China. You can find me with @YeDingding at Twitter, Facebook, and Weibo. I'm the founder of Fencer.co, a missing simple and productive collaboration tool for product teams. I'm the organizer of RubyConf China. We will hold the 6th conference, RubyConf China, at November 1st and 2nd. So welcome to our parties, everyone. I'm also running a podcast program called Tiawa. It's targeting engineers and startups in China. Okay, now let's start my topic. So we all know that real-world applications are complex, especially enterprise applications. Our goal is to have a high load but low response time. This is the 3-tile client-server architecture most used in real world. And we have the front-end web server handling the requests from browser or client, and then proxy to the apps. The application server will accept those requests and interact with the database server for data exchange. And there are many studies to test where the performance bottleneck resides among those components we discussed just now. Based on the experience, following are the status of the performance bottleneck's probability in each of its components. We have seen that there are 44% of performance bottleneck appears in database server, and 32% appears in the application server, 14% in the web server, and 10% on the network. So this result shows that almost 76% of the performance bottlenecks appear in the application and the database servers. Identifying performance bottleneck source is important to optimize the application performance. As we can see, database performance is most critical for application performance, as this is the main culprit for performance bottlenecks. There are many poor performance costs in database, such as inefficient secure statement, wrong data model or improper data model design, ineffective database configurations, missing or inefficient index, small or inefficient data cache or query cache, and wrong concurrent model, and possible deadlocks. So let's learn those concepts to better avoid those problems. Every application starts with data modeling. This is the job of the database designer, turning users' requirements into the application data models. Let's see a simple example. Everyone here should be very familiar with this code snippet. It's a migration file creating the table called users with the attribute UID, name, email, confirmed, avatar, basic info, and account ID. And we define several constraints to our schema, such as name should not be none, confirmed should be false by default. It's called integrity constraint in database. Integrity constraint are lists of predictions we add to ensure that changes made to the database do not result in a loss of data consistency to protect from accidental damage to the database. So let's turn back to our examples. It will create a primary key called ID for user table, and we will know that the ID field is an auto-increment field, which always has value. This is called primary key constraint, also called entity constraint. The second kind of constraint is not non-constraint because we're marking the name of the user should not be none. The third kind of constraint is Unicode constraint, saying that the UID field should be Unicode across the table. The fourth one is the referential constraint, ensuring that the account ID of the user should also appear in account table. So database itself has those constraints. Active Record claims that those intelligence should belong to in your application models, not in the database. So that's why we use validations and dependent to enforce data integrity. And the benefits in doing so is when we do it in the application level, we can easily customize the error message when the constraint is violated. So such as not none constraint with validates presence of, and Unicode for validates uniqueness of, and referential constraint use validates associated. So let's talk about referential constraint a bit more. Before we create and record the user, we want to make sure that the associated account record exists. After record created, what happens if we delete the account? If without any control, the user record will be left in dirty state. And because it can't find the account anymore, which will void the referential constraint. And this will cause bugs in our application. So that's why we use dependent to control what happened to the shared object when the account is destroyed. There are several available options as follows. So for delete, destroy, and delete all, means it will delete all the associated users to also be destroyed or deleted. This is on delete cascade on the database table schema. And for notify means that it should be set the account ID of the user to nil, and that will cause callback are not executed. And restrict with exception and restrict with error means the error or exception should be raised if there are any associated users, so account should not be destroyed. That's on delete restrict on the database create table integrity. So, however, it's still possible that we will violate the referential constraint if we use statements such as account.delete ID, because no callback will be executed. It will generate a secure statement directly. And including no callback will be executed, including the dependent associated action. So if we need real foreign key support, we should use the gem foreigner. And it's included in the Rails 4.2 by default. So let's talk about another topic, view. It's not the view of MVC, it's a database view. View is not used a lot in Rails app, but it can be very useful for proper situations. Basically, view is just a visual relationship of a query. Let's take an example. So seeing that a user can belong to many projects, and it might be the member of a project or the administrator of the project. So now we have the requirements to get the list of members the user can manage. So I define a function called admin user in user model. This is printing as this, so we have seen that it's a join statement, and it's a long where statement, including a in statement and a subquery. So this so it's too complex, and the code smell is not as good. Then how should we refactor? By creating a view, things will be much easier. So this is, we can create a view directory and reflect the relation among the users. This is the view definition. It's similar to the SQL generated in the last admin user section. So there are several points I want to mention. So first is the create or replace view, user project/membership. So it's the view name. And we have select. So we only select the fields we need, which is the user ID and admin user ID and project ID. And we have the interjoin. So it's a subquery, but we mark it as a temporary table called admin memberships. So when we have this view, we can refactor our code using, we define, because the view active record triggers views are similar as tables, so we can have a user project membership class which inherited from active record base. And it will use the view directly, and the active record will trigger view as no difference as the table. So, and then we has many associations which can directly fetch admin users. So these benefits Vue has bring to us. It gives us a simple and customized interface. And what's more, the index on the original table can still be used, which is really good. However, be aware that the Vue is not a real table. It's run every time Vue is referenced in a query, and most of the time, Vue is not insertable, updatable, or deletable. So if it's best suited for select, so you may concern that the performance is not very good because the query of Vue definition is run every time when it's queried, referenced in a query. So in secure standards, there are another kind of view called materialized view, which will execute the query and store the result into the view when the command is issued. So we can directly fetch the table results without additional query. It's prefetched. We use create materials view table name to create a material view. However, as the query is prefetched and executed once the command is issued, it will not be automatically updated unless we call the refresh material view manually. Refresh view. So material view is best suited for relationship really changed, such as reporting. And you can store, so for example, you can store yesterday's project states into a materialized view to cache the result instead of query the results every time when it's called. That's the use case of material view and the view which can bring benefits to us. So let's talk about another topic, which is index. Recall the performance bottleneck source. It says that nearly 10% of the database performance problem are caused by missing ineffective or inefficient index. Indexing is the primary mechanism to get improved performance on a database. So if given a table, do you know which index should be created? Is there any rules to create index? What's the trade-off? So let's first see how indexes work in database internally. So now giving a user table with the following records, what if we want to find a record whose ID is 4? Suppose without any index, the operation will search the record one by one, comparing its ID to 4 until find the record. So first, it's asked whether it's 4. Second, it's 4, no. Third, it's 4, no. Fourth, yes, so we find the record. We call it as a 4-table scan. Imagine when we have millions or tens of millions of records. This will be very inefficient. That's why we need the index to call it to speed up. With the index on ID field, which is by default for the prime key field, we can directly locate the location of the record and then fetch it directly. So it contains 2 steps. First, we get the pointer of the set record from the index table, and then we get the exact record using the pointer. So now the question is, how to get the pointer of that record quickly from the index table? There are several algorithms we can use. It's called index type in the database. Each index type uses a different algorithm and best suited for different types of queries. B+tree is the most widely used in almost all the database. Hash is another type which is supported by PostgreSQL and MySQL. Besides that, there are still other types such as GIST, SPGIST, and GIN. Today, I will talk about B-tree only. So B plus tree is a kind of balanced tree. This image is a 4-degree B plus tree. From the image, we can see that from a node in the left side, it's the value key value which is less than the key in the node, and in the right side is larger or equal to. So here I don't want to talk about how this tree is constructed. Let's see how we can use this tree to search for records to get the pointer of the record. Suppose we want to find a record whose ID is 4. It will traverse the path from the root node to the leaf nodes. First, it will try to find the 4, and by comparing to 5, it's smaller, so it will go to the left side. And comparing to 2, it will go to the right side. Okay, then it finds that we have reached to the leaf nodes. We will just bring this whole block into the memory and then iterate the records one by one. So from 2 is 3 and it's 4. Okay, we find the record. And then we get the pointer of the record and then use the pointer to fetch the record directly. So the algorithm complexity for a 4-degree tree is log 2n. So n is dependent on how many records we have. For example, we have 8 here, so it takes 3 steps to get to the leaf nodes. We can choose another degree as you wish. For example, now we use 4, and we can use 6, 16, 100, 1000. It depends on the index field of this index, on the type of the field, which is tree index. And the complexity of algorithm is log n tree, the depth tree r and n. So we can, even with millions of records or thousands of millions of records, the depth is not very high, and we can search it in the few steps, which can be very efficient. So from the example, we can know that B plus tree is very useful for queries like equal, and for queries with compare, such as less than. For less than, it will just find the value of 4 and then to traverse backward. And for the between, it will find the V at the tree, and then will iterate the disk block one by one to find till reach VR. Also, for the larger than, find the value and then iterate the leaf nodes one by one. So from this image and the explanation, we can know that B plus tree is very suitable for fields whose values of rise. And so if the field just contains 4 values, such as the Boole value or enum fields, the index will be a bit useless because there are many duplicates, and the depth will be, so it will almost taken like a 4-table scan. So in the implementation of some database, once the index field are with lots of duplications, the database will automatically turn to use a 4-table scan instead of the index. So after knowing that, should we create the index as much as possible? So before answering this question, we should know that there are several downsides of the index we should be aware of. First, each index we created will cost additional storage space. However, as nowadays, the storage is very cheap, is a marginal downside which you should not concern. Second, it will take additional time to create this index when record created. So it will slow down the record creation. This is a medium-level downside, but it's not a big problem. The third downside is the main one we should take into consideration while creating index. Index maintenance is costly if the values index updates frequently, and it might be offset benefits than having index. Because the maintenance will take 2 steps to the B tree construction. It first will delete the value and then add it back. So if the database updates the field value frequently, it's not good to have the index than not. So after knowing those downsides and know how index works internally, we can now get some conclusions about how to pick up index. First, it will depend on the size of table. If the size of table is small, for example, it just contains some hundreds or thousands of records, there will be no much difference between indexing and a full table scan. And a database such as PostgreSQL will choose to use a full table scan directly to search the records one by one, even if there are available index to use. Second is the data distributions. Indexes are only effective when the values of field is dense. Third is the query rate comparing to the updated load. Because index maintenance is costly, as we just discussed in the downside, you shouldn't create an index whose values are changed frequently, but not query too often. So that's the rules how we to pick up index. Then we turn transaction. Talk about transaction. It's another important concept in database. Transactions is a unit of program executions that access and possibly update various data items. Understanding the concept of a transaction is critical for understanding and implementing updates of data in a database. So let's see a real example in Rails first. Suppose now we want to update the field, the name of the user, and the user has a precise validation or name field. So from the generated SQL, we can see that it starts with a begin statement, and then do the job to update the name, and then a commit statement at the end means that the transaction is succeeded, and it has saved into the database. The second example is ended with the rollback because it has violated the name constraint, and then it claims to give up the update operations. Begin, commit, and rollback are the control unit of the transaction in the database. These two examples are single statement, and we can use the transaction class method to run multiple statements in one transaction. So this example, when we have the transaction class method, and we'll do two things. It will begin statement and run statement 1, statement 2, and then commit. So that we batch update the name of field, the active project ID in batch, so in one transaction, so to speed up. One interesting about transaction are callbacks. I know many developers are confusing why after save is not able to see the records from another process. For example, when we trigger a background process job in the after save, and it's execute such as in the sidekick and execute, and it can't find the record ID, the ID of that record, and it will raise error. That's possible. You might be possible have meet this situation. So if we know how transaction works, it's easy to understand why. When save and destroy code, it's automatically wrapped in a transaction, and the callback chain will be like this. So when we try to save the user, it will start with the begin statement of the transaction, and it will be run before save, callback. And the third step is the real save step. And the fourth step is the after save step. And then it's the commit step statement. So when after save is called, the transaction is still not committed. That means in another process, it might be not being able to see the change you made to the database. So it can't find the record, and it will just raise the record not found. And the final step is the after commit step. So if you really need the background job, such as some works to do, making sure that the record has been updated or created in the database, you should use the after commit callback. So indeed, transaction management is very complex in the database design and implementations. The database system should follow the ACID property of the transaction. A is the automatic, which means either all operation of the transaction happens properly in the database or none happen. So record the batched transaction we just use, if one of the statement of save field, the whole transaction should be rollback. So the future cannot leave the database in a state where a transaction is partially queued. So consistent is the execution of the individual transaction should preserve the consistency of the database. So if the state of the database before the transaction is consistent, after the execution, the state should still be kept consistent. So it should not be changed the state of the database before and after the transaction. I is isolation. It should ensure concurrent executing transaction should be isolated from one other, just like no other transaction is executed concurrently. D is reliability. It makes sure that once the transaction has completed successfully, the change has made to the database should persist, even if there are system features. So let's see an example to understand how this ACID works. So the complexity comes from the concurrent processing, like our Rails application might update the same table or record at the same time by different process or threads. For example, so this is transaction 1, which try to update the user record 3. And meanwhile, there is another transaction, T2, trying to read the user record user. So after as those two transactions are running concurrently, so what's the returning user record from T2? What does he say? Is the first post statement the same as the second post statement? Is there anyone want to guess? So if you think it's the same, please raise your hand. Anyone? So the same two post statements return the same results. Okay, I will leave us several seconds for you to catch the code. And do you think it will return the different statement, different results? Anyone want to raise a hand? Think it's different? I think no answer is correct because the answer is dependent and might be the same, might not depend on the different concurrent model or transaction isolation level. So there are several isolation levels we can use. So the first is read committed isolation level, which is by default in PostgreSQL. So read commit means that when I run a statement, the statement can only say rows committed before it begins. So let's take the example and to explain. So when the first find in transaction 2 is executed, the transaction 1 is already is not committed and it not updates the value. It's not updated the name value. So it will print the old value, and when after the sleep, it will find the value, find the record ID with 3 again, but the transaction 1 is already committed, and so transaction 2 will get the new updated record. So the second input, it will print the different value, as the first was old and the second will be printed the newest name. So this is for the read committed. It's by default at PostgreSQL. So here is another isolation level, which is by default in MySQL. Repeated read means all statements of the current transaction can only see the rows committed before the first query or data modification statement was executed in this transaction. So when the first query is executed, it will save the snapshot into the database memory, and the following queries will just use the snapshot. So using that, let's back to the example. When the first find of transaction 2 executed, it saves with a snapshot, and for the queries in the same transaction before the commit statement, it will always return the same record. no matter whether there are other transactions updating the record or not. So in the transaction 2, the second post statement or the second find statement will always return the old value when the first statement is executed. So it will return yes. So if the transaction at solution level is repeatedly read, it will return the same value. And this is by default in MySQL. So it acts different in MySQL and PostgreSQL. So you should know that when you use the proper database and to know how transaction works. The third is the serializable isolation level. Serializable is similar to repeatable read, but the transaction, just as the name, the transaction will run one by one. So let's use back to the example again. So it will, as it's run serialized, so the other transaction will only start when another transaction is completed. So no matter whether transaction 1 is run first or transaction 2 run first, it will always run only one transaction and it will return the same value. But it will vary whether it might be the old value or the new value, depends on which transaction is run first. So there is another isolation level which is called read uncommitted. Read uncommitted means that the transaction can always read the value not committed. So the changes are always visible. So back to the example we just showed. So no matter whether the transaction 1 is committed or not, the transaction 2 can always read the value. And it's the most useless isolation level, which we should never use because it will get the unexpected results. And PostgreSQL doesn't support this level, but it will just treat it the same as read committed. Okay, so that's all the thing.